so inferential statistics again, using or making an inference about the population from data that you've collected or whatever it happens to be. Probability experiments. A probability experiment is an action or trial through which specific results, counts, measures are obtained. So when we did the M&M's thing at the start of the year, that was a probability experiment. Focus on writing. No, you weren't. So when we did the thing with the M&Ms, that was a probability experiment. We were figuring out what was the probability of getting the different color M&Ms out of the bag. We set and flipped a coin. If I had you set and flip a coin 50 times each, is it going to come up 25 heads and 25 tails for everybody? Probably not. All right, so that's a probability experiment. Doing that, seeing what we get. The outcomes, the result of a single trial. So if we were going to flip a coin, it'd be the result of that one trial, of that one time that you did it. That's an outcome. It'll make me come over here and kick you every couple of seconds.
Is he asleep?
No, he's just not writing anything, he's not paying attention. Then when it comes test time, when we have a test over this, I'm saying, hey, you're allowed to use your binder, maybe. And he ain't gonna have nothing in there, and then he's gonna be crying to Marty that, oh no, I'm not doing well in Eversoul's class, he's mean. You wouldn't do that?
I would.
That's why I got pictures of you sleeping on my phone, so I don't.
It's okay. I tell my mom. She yells at me, but that ain't gonna help my eyes stay awake in class.
Sample space. The sample space is the set of all the outcomes. Sample space, very, very important in probability, because you have to know that sample space, because that's, if you're doing probability, that's going to be the bottom number of your fraction. All the possible outcomes. That's what's going to be on the bottom of the fraction when you try to find a probability. So sample space, very, very important. Finding the sample space. Sometimes it's easy, sometimes it's a little more difficult. If they tell you that there's 1,000 people that they surveyed, then you know the total possible outcomes, or all the possible outcomes, is those 1,000 people. If you're flipping a coin, the sample space would be a head and a tail. If you're rolling a dice, your sample space would be 1, 2, 3, 4, 5, 6. If we were doing the pizza thing, like I mentioned earlier, a little harder. Event consists of one or more outcomes and is a subset of the sample space. Subset, key thing there, it's a subset of that sample space. So we could say our event, if we're rolling a die, maybe our event is to get a number lower than 4. Well, then it could be a 3, it could be a 2, it could be a 1. So there's more than one possible outcome, but it doesn't have to be more than one. It could just be we want to get exactly a 4. So event and outcome are two different things. All right, an outcome is just a single trial that you're doing. An event is what you would like to happen, or what you're looking at to happen.
Is that what subset means?
Subset means that you're taking part of this. So if our sample space is is this big circle here. A subset is just, part of it. So if we were doing like, if this whole big circle was dogs, and we wanted just poodles, this would be our event that we want, that we're looking at, and the dogs is the whole sample space. And then a single trial or single outcome is us picking a dog, and we pick Rex.
Oh, what was my dog's name?
Alright, so alright, this is what a tree diagram looks like. Just write tree diagram. Don't draw all of this, but give yourself an idea of what a tree diagram looks like. This tree diagram is actually for like looks like it's for maybe a little deli shop or something. They have two choices for drinks. That's your first thing. So that's your drinks. What drink you could pick. Then they have three choices for bread. And then it looks like that they have 4 choices for their sandwiches. Like I said, don't write it all. What would be a good idea here? Maybe put like a 1 and a 2 here. Put some branches off of that one. Put some branches off of that one. Maybe put 4, 5, 6, 7, 8, 9. Put some branches off of this one. That's what a tree diagram looks like.
Oh my.
All of these out here, this whole list, this is our sample space. That's all the possible outcomes. We could pick a soda with bagel, cheese. We could pick juice, rye bread and cheese, so on, so on, so on. Those are all the possible choices that we had at that deli or whatever it happens to be. If we were going to do the pizza thing that I talked about earlier, you might have what? What do they have different at pizza places?
Oh, pepperoni.
But what could you start off with?
Crust.
Oh,
You gotta have a crust, right? So you can say, okay, I got my crust, and maybe there's 3 different kinds of crust. And then you might go to your toppings, and you might have, however many types of toppings that come off of that. You could say, okay, I could have, just a cheese, could have just a pepperoni,
Deluxe.
could have and we don't want to put deluxe in there because then that's going to be on out here, and we're going to have a whole bunch more on there. So this would be, if we just had 1 topping, then if we had 2 toppings, you could go on out, 3 toppings, so on and so on. Alright, so what we want to do on this, you don't have to write this down, just watch. When it's written this way, somebody not, it says probability So when you see this, when it looks like this is how we write probability. Probability of whatever the event is. So it's probability of something. So if we were rolling a die and we wanted to get a 4, then we put probability with 4 inside the parentheses. Alright? If we're doing this one, probability that we pick soda, white bread with turkey. Well, we look down through here, soda, white bread with turkey is right there. Is that the only one that's soda, white bread with turkey? Yeah. So we want the probability of this is going to equal Well, what we'd have to do to find this bottom number is count up. Grant's telling us there's 24 of them, so that goes on bottom. How many opportunities do we have to have that soda, white bread, and turkey? Just one, so it'd be 1 out of 24. That's our probability. This book, I think, most of the time changes that probability into a decimal or a percentage. Either one would be fine with me, all right? How do I change that to a decimal? How do you change 1 over 24 to a decimal? Divide. All right, so you just divide it on your calculator, change it to a decimal. Usually we'll round it off to 2 or 3 places behind the decimal. And if we wanted it as a percentage, for whatever reason, then we'd change it to that by moving the decimal over 2 places. 4.1, so 4.1%. All right, probability experiments. Don't write this down. Just watch. With the probability experiment, if we were going to roll a die, we rolled the die and it came out a 3. Our sample space, 1, 2, 3, 4, 5, or 6, that's what we could have gotten. Those are all the possible outcomes. The event, maybe we want the die to come up on an even number, so that's the event we want. And if we want to find the probability, then we'd say probability that it's an even number. How many total possible outcomes, or what's our sample space? How many of them? 6. How many even numbers? And we reduce that down to 1/2 or 0.5 or 50% of the time, whichever one best fits the problem. Most of the stuff that we're going to do in here, the 50% or the 0.5 is probably going to be the one that we want. Usually just leave it as a decimal. Sometimes the percentage makes a whole lot more sense because people will understand that better. You say you're going to get that 50% of the time, it makes more sense to most people. A probability experiment, don't write this down. A probability experiment consists of tossing a coin and then rolling a 6-sided die. Describe the sample space. Maybe the best way to describe this sample space is maybe to use a tree diagram. So watch, I'm going to show you how to draw a tree diagram to figure out this sample space. If we toss a coin, what's our possible outcomes if we toss a coin? So we got a head. This is how you'd have to make the tree diagram. Head, tail. We tossed the coin and we got a head. Then we rolled the die. What could we get if we got a head with the coin? What could we get when we roll the die? Could get a what? 1. Could get a 2. If we got a tail when we flipped the coin, what could we get? Same thing, right? 1, 2, 3, 4, 5, 6. Now our sample space, we're going to list out here. We could get H1, we could get H2, we could get H3, we could get H4, H5, H6. I'm not going to list all of them out, but it'd be the same thing down here just with the tails. How many total are we going to have in our sample space? What's our total possible outcomes? 12. All right, so that's how.
What? Oh, never mind.
Because we'd still have these, right? T1, T2, T3, T4, T5, T6.
Is that row like necessary? Because isn't that like pretty much the same things?
Yeah, but to show the sample space, you'd need all of this. So if they ask you to list the sample space, this is what you need to list. If they ask you to draw the tree diagram, then you need that whole thing. How many possible outcomes were there? 12. A tree diagram looked like this. That's what we just had. I made mine sideways. They made theirs up and down. They're cute little pictures of a head and a tail there. Alright, a simple event, write this down. Simple event is an event that consists of a single outcome. So if we're looking for just a simple event, not something that's got more than one possible outcome, just something that's a simple event. If I wanted to pick a male out of the class, that's a simple event. If I wanted to just get ahead in a 3, that's a simple event. Something that wouldn't be a simple event was something like if I wanted to get ahead in a 3 or ahead in a 5. Because then we're putting in more than just one thing. So a simple event just consists of a single outcome. And the event that consists of more than one outcome is not a simple event. Very self-explanatory there, right? If it's got more than one thing, then it's not simple anymore. Determine whether the event is simple or not. You roll a 6-sided die. Event B is rolling at least a 4. Is that simple or not simple? Not simple? Not simple because we could roll a 4, 5, or a 6, so it's not simple. Alright, fundamental counting principle. Write this down. Just write this part. Just write fundamental counting principle. And then I'm going to write something else down here so you don't have to ignore that line there. Alright, what the fundamental counting principle is. Instead of us making a big long tree diagram for something like the pizza, if we have 7 different toppings that we serve at our pizza shop, and this is very, very important that you understand the fundamental counting principle, because it's going to give you tells you total outcomes. You might want to write that down somewhere on there. Fundamental counting principle tells you the total outcomes. Do what?
You didn't listen to that big thing, right?
Yeah.
Yep. I don't know, that's why I asked.
So it tells you the total outcomes. What you're going to do with it. You're going to take your first, whatever your first thing is that you're doing, maybe you're rolling a die, maybe you're flipping a coin, maybe you're whatever you're doing. You're going to take how many possible outcomes are in it. So you take it, how many possible outcomes. Your second thing, whatever it is that you're doing, how many possible outcomes. Third thing, whatever it is that you're doing, how many possible outcomes there are in it. So maybe Carson got up this morning and he had 6 shirts he could have chosen from to put on, 4 pairs of pants he could have chosen from, and 3 pairs of shoes. So maybe we have something like that. And we want to figure out how many different outfits he could have picked when he got up this morning. All you're going to do with those is multiply. You're going to multiply all those together, and that's going to give you the total possible outcomes for all those events. Makes sense, Grant? So you just take how many possible outcomes are in the first one, times how many possible in the second one, times how many possible in the third one. That's going to give you the bottom number of your fraction when you're finding a probability. Whatever that probability is that you're looking for. That's going to tell you your total possible outcomes. Total possible outcomes. Very important, because you don't wanna have to draw a tree diagram or something for a lot of these things, cause it's too much. And that's all this says. In one event, if one event can occur in M ways, so there's M possible outcomes for that first event. Second event can occur in N ways. Third event can occur in R ways. All we do is take M times N times R, and that's going to give us how many total possible outcomes there are. So Carson could have made 72 different outfits this morning, and yet he picked the one that he's got on. That just blows my mind. That's good. It's a little strange. All right, an example.
You paused it to say that and played it.
I said it again. You are purchasing a new car. The possible manufacturers, car size, colors are listed. So you could have a Ford,
Smart.
GM, or a Honda. Car size, you could get compact, you could get mid-size. Your color, you could have white, red, black, or green. We really do not want to make a tree diagram for this, because you're going to have to put Ford, GM, Honda, then off that come 2 branches for compact or mid-size, then off each of those come 4 other ones, which is going to be a pretty big tree diagram. So what we can do here to find the total possible outcomes, how many possible outcomes for the first choice? 3, 2, and 4, and we just multiply those together. 3 times 2 times 4. And what do you get?
So that's how that crap works.
And that's, so that would be your, if we said, what's the probability that you picked
23 times
GM, compact, white?
2. Backwards.
And by doing 3 times 2 times 4, it'll give you that answer.
It doesn't give you this answer. What's it give you?
The
Total possible outcomes, which is just the
You're right, Sean.
bottom. So 3 times 2 times 4 is 24. How many choices are there that's GM, compact, and white? Just one, right? There's only one choice of that, so it'd be 1 out of 24. What if you just said you didn't care about the make, but you wanted it to be a compact car in white?
12.
So how many different possible outcomes are there that have that in? 8?
I don't know, tell me how to do it. I just have to count.
2.
What are they? What are the possible ones? Could have what here?
4,
Could have Ford,
GM,
could have GM,
Honda,
you could have Honda. These 2 parts are going to stay the same, right? So how many different favorable outcomes are there? 3. So then it'd be 3 out of 24, which reduces to 1 out of 8. All right, so 24 is what we came up with. If we made a tree diagram for it, this is what the tree diagram would look like. It's too much to do. Now, sometimes with the tree diagram, let's go back to it. With the tree diagram, if you're actually looking for the probability like we just were, we know that there's 24 possible outcomes, but if we made the tree diagram, then we could see that, hey, here we got a Ford mid-sized white. That's one of the cars that we wanted. Or no, we said compact, didn't we? Compact, not mid-sized. GM compact. Yeah, that's wrong white. GM compact white and Honda compact white. Then we can look and see, hey, there's only 3 possible ones that we could pick then and get that top number. Pizza Place has 3 kinds of crust. 12 times 12 toppings and 3 kinds of cheeses, how many different one-topping pizzas could be made? So how many choices do we have
3.
for
Crust.
the crust? 3 times
12.
12,
There's 108.
3.
108. Now this is a little tougher.
2 toppings.
What if we're doing 2 toppings?
Oh boy.
How many choices you got for the crust?
3.
How many choices you got for the first topping? 12. How many choices for the second topping? Now 11, because you already picked one of the toppings, right? How many choices for the cheese? That would tell us the total possible 2 topping pizzas. 1188.
So,
Now again, this isn't probability, this is just the total possible outcomes, right? So if we wanted to do probability and we wanted a thin crust, pepperoni and bacon with mozzarella cheese, our probability would be 1 out of that because there's only 1 pizza that's going to be made that way.
so where did you get 11 from?
Because if we had 12 toppings, all right, and we used one of them, we put pepperoni on there already, but now the pepperoni's not a topping that we're going to put on there anymore. Well, then we'd have to, then we'd just say pepperoni again, all right? So we got 12 toppings, we took one of them away, so now we only have choice of 11 different toppings. So if we wanted a 3 topping pizza, you'd still have 3 crusts, 12 choices for your first topping, how many choices for your second topping? How many choices for your third topping? So on, so on, so on. And we could figure out all those different. So just think with a pizza place, go to Pizza Hut, how many different possible pizzas could they make? A whole bunch. All right? Probably in the millions. There's all our answers that covered up. All right, types of probability. 3 different types of probability. Classical probability, classical or theoretical probability, each outcome in the sample space is equally likely. In other words, if I was going to pick one of your names and give you 10 bonus points, it wouldn't be classical probability if I left out Sean's name because I decided I didn't like him that day. All right, so everybody's got the same possibility of being chosen. Find classical probability. Use this formula. And instead of writing all this out, you might just write favorable, 1 second, favorable outcomes, and on bottom, total outcomes. Favorable outcomes, total outcomes. When I say favorable outcomes, sort of not a good word to use because favorable outcome means something that you want to happen. It might just not be what you want to happen. It might be something that you're just looking at to happen. Probabilities can be written as fractions, decimals, or percents. Again, I think this book most of the time gives their answers as decimals. I would rather see a fraction or a percent because more people understand those. The reason that you don't just leave it as a fraction, we just had that one a second ago with the pizzas, and it was 1 out of 1,189. Is that fraction going to make sense to anybody? No.
Definitely 1188.
All right, it was 1189.
Mr.
It was
Ed.
88.
Was it really?
Yeah.
All right, so it wouldn't make sense to anybody to say 1 out of 1,188, so we probably want to change that into a decimal or a percentage. Say the percent of picking that certain pizza is whatever it came out to be.
Jesus,
That's what the book uses.
that's a very big decimal.
Book uses, it's not a very big decimal. There's no such thing as
Very little decimal.
There's no such thing as a very big
Sorry.
decimal.
It's got a lot of numbers in it.
It's got a lot of numbers, thank you, but that doesn't make it big. Alright, example, you roll a 6-sided die, you want to find the probability of each event. So event A, rolling a 3. So we want to find the probability of rolling a 3,
1/6.
1 out of 6. See, to me, it's just easier to leave that as a fraction, because that's a pretty easy fraction and everybody understands it. Event B, rolling a 7. What's the probability of rolling a 7?
Is there a 7 on the dice?
Really?
So it'd be 0.
Oh.
No, it wasn't.
No.
Probability of rolling a number less than 5. Be careful. So we want less than 5. 4 out of 6. What's 4 out of 6 reduced to?
2 out of 3.
2 out of 3. And you should always reduce it because then it makes more sense. Alright, so those are the probabilities. We could change each one of those into a decimal or percentage, but on something like this, with those low numbers, it makes more sense to just say 1 out of every 6 times you're going to roll a 3. Our sample space is 6. Notice here, because this is this book, they changed everything into a decimal. All right, empirical probability. Second type of probability, empirical. Do what? Say again, I couldn't hear. No, that's different, empirical. That's an empirical rule. So empirical probability is based on observations obtained from a probability experiment. When insurance companies come up with a probability to what to charge each age group, they do it based on what they've seen in the past. When we did the M&M's experiment, we might open up another bag of M&M's and say that, all right, we expected, and I think we did that, didn't we? That we expected that 2 were going to be this color and 3 were going to be this color, and somehow we came up with like 25 M&M's, and there was only going to be like 8 in the bag, and because you guys couldn't add very well. All right. With empirical probability, this is the formula. Frequency of the event, whatever it is, over total frequency. Frequency of the event over total frequency. Same thing. All right. How many times the event's going to occur, how many favorable outcomes there are compared to the total. It's just on this one, you have some chart or something there to look at, and it says red, black, green. Maybe we set out on the street and we watch cars go by and we calculate up. We sit here and make a tally. Okay, there's been 5 red cars, and we just tally them up, and we figure out that total when we're done. That's what's going to go on bottom. And then the probability that they were red We look at how many reds there were, and we figure wherever we go set on the street, that's gonna be the probability of red cars that go by. So it's just using empirical probabilities, just using some kind of experiment or some kind of survey or whatever it happens to be. Most of the stuff that we do will be classical probability, because I'm not going to have you go out and stand on the street, because we know that some of you are intelligent enough to stand close to the street. Mommy get upset with me, get ran over or something. So it'd be something like this. You'd be given the chart, the response, serious problem, moderate problem, not a problem, number of times it occurred. Got the total down here. Remember, this little symbol means summation, so that's all of them added up. That's going to be our bottom number. What's the probability that it was a moderate problem then? What goes on top? 115. And fractions like this are better to change to a decimal. Just grab your calculator and change it to a decimal, because that's going to make more sense than 115 out of 320. They wanted this one, they wanted, and I didn't even read the problem, they wanted a serious problem, so it was 123 out of 320. They changed it to a decimal and got 0.384. Notice they go out 3 places every time. If we wanted to change that to a percent, what would that be as a percent? .4%. That might make more sense to whatever the problem was saying, or whatever it was asking about, to tell somebody, hey, about 38% of the time, it's going to be a serious problem. Law of large numbers. Write this down. Write law of large numbers.
So this isn't still part of the whole types of probability, is it?
Not really.
I thought there was 3.
There's another one after this. In the law of large numbers, also write down the sentence after, because that's the definition of it. And there's no easier way to put it. Law of large numbers is an experiment that is repeated over and over. The empirical probability of an event approaches the theoretical probability of an event. So in other words, we sat here and flipped the coin 10 times. Are we going to get 5 heads and 5 tails? Probably not. If we flip it 100 times, are we going to get 5 heads and or 50 heads and 50 tails? No, but we're probably going to keep getting closer and closer to that. If we flipped it 1,000,000 times, the percentage would get closer to 50% every single time. And that's what it shows here. Here it shows a bunch of people flipping a coin so many times. They flipped it, looks like down here, they flipped it like 10 times. And then they got up, once they got up to about 150, notice the line started to be right at about 50% for everybody. All their numbers started coming together closer and closer. That's the law of large numbers. In other words, the larger you make your total outcomes, the closer you're going to get to what we theoretically say probability is. You roll a die, you're not going to get, you roll a die 6 times, you're not going to get each number once. You roll a die 600 times, you're going to be real close to getting each number 100 times. You roll it 6,000 times, you're going to be even closer to getting each one 1,000 times, so on, so on, so on. That's all the law of large numbers says. All right, subjective probability. This is the third type of probability. Subjective probability is what doctors use. Michael goes into the doctor and is getting checkup, and he tells the doctor, "Doctor, my head's been hurting all the time, and I'm not sure what's wrong. Doctor checks him out a little bit, comes out and puts a cast on Michael's arm, says, you got a broken arm, that's what's wrong. And Michael probably wants to get a new doctor, right? Doctors usually don't do this anymore. Used to be, if you watch some of the old TV shows and the stuff, they tell you a percentage. Oh yeah, they have a 70% chance of recovery. Most doctors don't do that anymore because that just gets them in trouble. Because if they tell somebody they have a 70% chance of recovery, then the people think that what's going to be the case? They're going to live, they're going to recover. That's not the case. If he's telling you you got a 70% chance of recovery, he's also telling you that you got what? 30% chance that you're not going to recover.
Dying.
All right? Weather people, everybody complains about weather people all the time. If it comes out and says there's a 40% chance of rain today, everybody thinks that it's going to do what? It's going to rain. Is that really the case? No, that weather person is saying there's a 40% chance it might rain, but there's a better chance, because there's 60% chance that it's not going to rain.
Like there was when we were in a Fort Concrete in Greenville. It's like a 3% chance of rain, something tiny. Started downpour and they changed it to 100% right quick.
So whenever, it always kills me because everybody complains about weather people. They're never right. No, they're right all the time. Every time they make a prediction, they're right. Because if they say there's a 40% chance of rain, then they're saying there's a 60% chance that it won't rain. Regardless of what it does, are they still right? Yeah. Sort of.
Just call it 50%.
But they're not wrong, are they?
Call it a 50% chance all the time.
That's what you could do. Now, where do weather people get that 40% from?
Yeah, that's true. Watching conditions that have happened before.
Exactly, and that's what they do. They look at, hey, if the humidity is this number, the sky is at this level, so on. What I don't know because I'm not a meteorologist, but they look at different things and they say, oh, when these three things occur at the same time, then it's normally going to rain. So it might be a 70% chance that it's going to rain. And they look at past things. So it's just an educated guess. Don't go over and tell the science teachers it's an educated guess because they'll tell you that's a stupid statement, which it is, but because it was on the PowerPoint that I didn't feel like changing.
Why does it have tails?
Do I? Classify the statement as an example of classical, empirical, or subjective probability. Probability that you will be married at age 30 is 0.5. Is that classical, empirical, or subjective?
Subjective. I don't know. Seems like an educated guess to me.
You think it's just a guess?
I mean, I guess something different probably, so.
Subjective. All right? It's most likely an educated guess because do we know for sure that you're going to be married by the age of 50 or 30? No, it's probably something that we just looked at what's happened in the past, and most people in the U.S. are married by this age. Probability that a voter chosen at random will vote Republican is 0.45. Classical, experimental, or classical, empirical, or subjective? Subjective again? I bet not subjective on this one.
Empirical.
I bet it's empirical because I bet they looked at how many voters are Republican, how many are Democrat, and just went from that, right?
I figured it was about 50.
All right, so probably empirical. Is it 50-50?
Probably not.
With the presidential stuff going on right now, you should know it's not 50-50, right?
Yeah.
It's more Democrats are probably closer to 60% than 55, but probability of winning a, this one's what?
Classical.
Classical. Because we actually just figured 1 out of 1,000. All right, range of probabilities. Write this down. Very, very important. Write down range of probabilities rule and write this down. That's what you need to write down. Probabilities always got to be between 0, no, I shouldn't say between. Always from 0 to 1.
He wants you.
What's 0? What's the probability of 0 tell you? Try some more. What's the probability of 0 tell you? So it can't happen. The event can't happen. What's the probability of 1 tell you?
It can happen, really.
We're talking about probability, and the probability is 0 means the event is never going to happen. What's the probability of 1 tell you?
It's gonna happen.
Happens every time. 1 tells you it happens every time. And most things fall in between there. If the probability of an event is 0.05, so 5%, 0.05 or less, we call it an unusual event. It's an unusual event. Just like with the empirical rule, if something was 5% or 95%, then it was unusual. If you're doing a sample space, all the probabilities for any sample space must add up to 1. So if we added up all the probabilities of rolling a die, well, to get a 1, it'd be a 1 out of 6 chance. Get a 2, it'd be a 1 out of 6. 3, a 1 out of 6. A 4, a 1 out of 6. A 5, a 1 out of 6. 6, a 1 out of 6. If we add all those up, what's it all going to add up to? 1 whole. All right, so all the probabilities of whatever you're dealing with always has to total up to 1.
So should I put that like number one thing?
That's up to you. This is sort of all the stuff that I just said. Probability 0, it's impossible. If it's down this way, then it's unlikely that it's going to happen. The higher it gets, the more likely it is it's going to happen. And if it's at 1, it's most definitely it's going to happen every single time. So if I said, what's the probability of rolling a 7 on a die? It's not going to happen. 0 out of 6. If I said, what's the probability of rolling a number smaller than 10 on a die? Probability is going to be 1. It's going to happen every time. All right? All right, complement of an event. Go ahead and just write this. It's no real simple way to put this. Complement of an event is all the other stuff outside the event. So if our event is here, this box is all our total possible outcomes. All this stuff out here is the complement of it. And we symbolize complement by this. It's got that little tick mark on it. So if we want the complement, they might write something like the complement of, yeah, they probably wouldn't write it that way. Maybe they don't want 1 to occur, but they want the complement of 1. So they might write something like that with that little tick mark on it. outcomes, or all possible outcomes, all right?
Okay.
That's the box. The circle is the event that we're looking at. Maybe rolling a 6 on a die, all right? So 6 would be inside that circle. That's that event. What's the complement of that? What's the other outcomes that we could get other than a 6?
The rest of them are
So 1, 2, 3, 4, or 5. That's the complement. That's the stuff outside the circle. Yeah, that's a complement. So if we wanted, if we were going to pick from you guys, and I said we were finding the probability that we picked Nick, 1 out of whatever. Well, if we wanted the complement of that, then who would be in the complement?
all of us.
Everybody else besides Nick. Alright, so it was 1, 2, 3, 4, 5, 9. 9 of you in here today. Well, then the probability that we get the complement of Nick, I can't remember how this book, if they just do it outside there or if they put it in on Nick or whatever. Well, get Nick is 1 out of 9, then the complement of that's got to be what? 8 out of 9. It's just whatever's left over. E prime, I can't remember what that's called. That's called a prime on a tick mark. Pretty bad one, I can't remember what it was. Might want to write this down even though I've written all over it. Let's do this. Let me erase everything on this slide. Might want to write this right here down. Probability of E prime plus probability of E always has to total up to 1. That's what we were just talking about with Nick there. And the other way that we can do it, probability that we get Nick should equal 1 minus the probability. So on ours it'd be 1 minus 8/9, which is 1/9, and that would tell us the probability that we picked Nick. So if they ask you to find the complement of an event, you can find the probability of the event and then just subtract it from 1, or you can say that the two, the complement and the event, have to add up to 1 and find whatever you need to do that way. They switch it around again. It doesn't. Those are all the same kind of setup. You survey 1,000 employees in company and report the age of each. Find the probability of randomly choosing an employee who is not between 25 and 34. Well, we look down here. The probability that they are between 25 to 34, is 366 out of 1,000. Do we really have to go through and add up all the rest of these? No. What we can do with that is know that, hey, there's 1,000 total. So to find the complement of that event, we just take 1,000 minus that, which is what, 634 out of 1,000. So we just took this number, the one that we didn't want, because we said not between that. That's the complement. We get 634 out of 1,000. So probability that it was that's what we said. Complement rule is 1 minus that, 634 out of 1,000. You got 0.63. And you could have, if you changed it to a decimal here, you could have just said 1 minus that on your calculator and got this answer and not even have to deal with the fraction. Probability using a tree diagram. Probability experiment consists of tossing a coin and a simple spinner. Use tree diagram to find the probability. We're going to do this. Our tree diagram is going to look something like this. Could get a head. What could we get on the spinner? 1. We could also get a 2, 3. Random wants to make sure that she goes in some kind of order, right? Because if you're making the tree diagram and you just start jumping around at random, are you going to get lost? Probably so. 5, 6, 7, 8, all the way up. We could get a tail, same idea. I'm not going to do that whole thing. Our tree diagram would look something like this. Maybe it's easier to draw a tree diagram this way. It looks like it probably is, because I always run out of space. If we want the probability of tossing a tail and spinning an odd number. Well, if we do a tree diagram, then we can go through here and say, okay, we want a tail and an odd number. And we can just circle the favorable outcomes. So we can circle what's going to go on top. Well, tail, odd number, tail, odd number, tail, odd number, tail, odd number. How many favorable outcomes are there? 4. How many total outcomes in our sample space? 16. Reduce that down, and it's 1/4, which is 0.25, right? 25% of the time. That's what they did there. So, using a tree diagram sometimes makes it easier if you can draw the tree diagram fairly quickly, because then you have all the possible outcomes and you can just look at them and say, okay, that's not a favorable one, that's not favorable, that's no. And you can just circle the favorable ones and figure out which ones are what you want and how many total there are. Using the fundamental counting principle. Your college identification number consists of 8 digits. Each digit can be 0 to 9. And each digit can be repeated. What is the probability of getting your college identification number when randomly generating 8 digits? Do we really want to go through and make a tree diagram for that?
No.
No. All right. So what we do for the first number, how many possible outcomes for the first number?
9.
Is it just 9?
10, it's 10.
It's 10, isn't it? How many for the second number? 10. Third number?
10.
Fourth number? Fifth number? Since they said they can repeat, it's just going to stay 10 every time, right? 3, 6. And that means Grant's saying it's 10 to the 8. You could punch that into your calculator and figure out what that is. Do what?
I didn't see 10 next to the equals. I was like, it's 7.
Wait.
First number could be any of those numbers, right?
0 through 9.
So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 of those numbers. So there's 10 possible things for the first number. They said it can repeat. So even if you pick a 2 the first time, you could get a 2 the second time also. So 10, 10, 10.
So like, but if you couldn't pick a 2,
Then this would be 9. This would be 8, 7, 6. And that's more like the lottery. Alright, the lottery, because once the ball comes out when they blow it up through that little tube on TV at 7:30 at night or whenever it is, that ball can't come out again, right? So if there's 10 possible outcomes, now there's only 9, then 8, then 7 for every one they pick. So 10 choices for each of the 8 digits. Do that, get 100 million. How smart Graham is. Wish I could keep him that smart all the time.
There's some big things.
If we want the probability that it's your exact ID number, how many different ID numbers are there for you? 1. So it'd be 1 out of 100 million.
The Social Security's got 7 or 9 digits.
It's got,
There's 8.
it's 9. Yeah. That's 9. It's got, it goes 3, 2, 4.
Oh, yeah.
So 1 out of 100 million. All right, odds. Write this down. Odds very important. Odds
No, is this
sort of
E?
confusing.
Okay, hold up. I think I just discovered something. I mean, not really. So the E that we're talking about, is that?
No,
this?
that's completely different. That's the E. That's the E on your calculator is telling you that you're using scientific notation.
Okay.
So that was saying 1 e to the negative 8. What that means is it's 1 over, and then on the bottom, 1 with 8 zeros. Since it was negative, tells you it's on the bottom of the fraction, and this tells you how many zeros you have.
Okay.
If it was a positive 8, then it'd been 1 with 8 zeros, and you wouldn't have a fraction.
Serious question. Are we the only country to use social security numbers, or is everybody use that?
They probably got some kind of number. Switched on me the other.
Ooh, yeah.
Alright, so the odds. Odds of winning, when you do odds, it's written this way. You gotta make sure you know this because odds is a little different. You got successes compared to unsuccessful. And I usually write this: win, how many times you're gonna win compared to how many times you're gonna lose. If you're watching horse racing and they say the odds of a horse winning is 2 to 5, what's that telling you?
2 minutes on
They're going to win 2 times, lose 5 times. How many races is that horse going to run? 7 total. All right? 7 total. So 7 total. You got to be able to figure that out. So if I wanted to change odds into a probability, what's the probability that the horse is going to win? If I'm looking at this right here, 2 out of 7. All right. So odds is written just with wins compared to losses. If you're looking for the odds that you're going to lose, then it's written the other way around, and it's losses compared to wins. So when if you're at the horse track and you're betting on a horse, and they're 4 to 1, you really want to bet on them? No, because what that's telling you, they're going to win. They're probably going to win because they're going to win 4 races out of every 5 at that certain track. But when they pay you off, they also go by that. So for what this is also telling you is for every $4 that you bet, they're going to pay you back $1. So if you bet $40, they're going to pay you back $10. So you're still winning,
You want my fill to 10.
but you're not. No, you don't lose your $40. All right, you still get it also. So you just get 10 on top of it, but you don't win very much. Right. You don't see. The bad thing with this is, so you're putting up $40 for a chance to win $10, but you're also putting up $40 with a chance to lose 40. So you could lose 40 and you could only gain 10. That's not really a.
Porky won like 30 grand.
Who? Who's Porky? All right.
On that American Pharaohs, you know him, this Egypt fetish. He would bet like 10 grand on that horse.
All right. This is what we covered. I'm just gonna skip over that. I didn't think. Yeah, I'm not gonna see. This is your assignment.
He's in jail.
I was gonna say I didn't think Mr. Pennington was doing real well.
Well, this was before.
Where'd he find 10 grand to even